Our universe is a vast and mysterious place, filled with wonders that boggle the mind and stretch the imagination. It's full of incredible objects, each more fascinating than the last, from the swirling clouds of nebulae to the dense clusters of stars. One of the most fascinating objects in the universe is the star. These celestial bodies have captivated human curiosity for millennia. Stars are giant balls of hot gas, primarily hydrogen and helium, undergoing nuclear fusion in their cores. They emit light and heat, which travel across the vast distances of space to reach us here on Earth. We see this light from Earth, twinkling in the night sky, guiding sailors and inspiring poets. It's how we navigate and explore space, using the stars as our cosmic landmarks. Stars are not spread evenly throughout the universe. They gather in vast, gravitationally bound groups. These groups are called galaxies, each containing millions or even billions of stars. Our own galaxy is the Milky Way, a sprawling collection of stars, gas, and dust. It contains billions of stars, each with its own unique properties and potential for hosting planets. Our Sun is just one of these billions, a relatively average star in the grand scheme of the cosmos. Stars have a life cycle, just like living things. They are born in the dense regions of space, live for millions to billions of years, and eventually die. They are born in stellar nurseries, live through various stages of fusion, and die in spectacular events like supernovae, leaving behind remnants like neutron stars or black holes. Understanding their life cycle helps us to understand our place in the universe, shedding light on the origins of the elements that make up our world and ourselves. Stars are born in giant clouds of gas and dust. These clouds are called nebulas. Nebulas are some of the most beautiful objects in the universe. They come in many shapes and sizes. Some are illuminated by the light of nearby stars. This makes them glow with vibrant colors. Nebulas are formed when old stars die. When stars run out of fuel, they expel their outer layers into space. This material then clumps together under its own gravity. Over millions of years, these clumps grow larger and denser, eventually forming a nebula. Inside a nebula, gravity pulls gas and dust together. These particles clump together, growing larger and denser over time. As the clump grows, its gravity increases, pulling in even more material. This process causes the core of the clump to heat up. Temperatures and pressures become extreme. When the core reaches a critical temperature, a process called nuclear fusion begins. In nuclear fusion, hydrogen atoms fuse together to form helium. This releases tremendous amounts of energy, which creates outward pressure. When this outward pressure balances the inward pull of gravity, a star is born. Once a star ignites nuclear fusion, it enters a long, stable period called the main sequence. During this phase, the star fuses hydrogen into helium in its core, releasing a steady stream of energy. This energy is what makes the star shine. The length of time a star spends on the main sequence depends on its mass. Massive stars burn through their fuel much faster than smaller stars. Our Sun is about halfway through its main sequence lifespan, which will last for about 10 billion years. Section 5. Red giants. Stars age out. Stars, like all things in the universe, have a life cycle. They are born, they live, and eventually, they age and die. This chapter delves into the fascinating process of how stars age out, transforming into red giants. Eventually, a star will exhaust the hydrogen fuel in its core. This is a critical turning point in the life of a star. Without hydrogen to fuse into helium, the star can no longer sustain the nuclear reactions that have kept it shining for millions or even billions of years. As this happens, the core contracts and heats up. The increased pressure and temperature in the core ignite a new series of nuclear reactions. These reactions are different from the hydrogen fusion that powered the star during its main sequence phase. The outer layers of the star expand and cool, causing the star to swell into a red giant. This expansion is so vast that if our Sun were to become a red giant, it would engulf the inner planets, including Earth. Red giants are much larger and cooler than main sequence stars. They can be hundreds of times larger in diameter, but their surface temperatures are lower, giving them a reddish hue. They often appear reddish in color. This is due to the lower surface temperature, which shifts the star's light towards the red end of the spectrum. During the red giant phase, the star's core continues to contract and heat up. This ongoing contraction increases the core's density and temperature, setting the stage for the next phase of nuclear fusion. Eventually, the core becomes hot enough to fuse helium into heavier elements, such as carbon and oxygen. This helium fusion process releases a tremendous amount of energy, which further fuels the star's expansion. This process releases even more energy, causing the star to become even larger and brighter. The red giant phase is a spectacular but relatively short period in the life of a star, lasting only a few million years compared to the billions of years spent in the main sequence phase. As the star continues to evolve, it will eventually shed its outer layers, leaving behind a dense core that will become a white dwarf, marking the end of its life cycle. Section 6. Planetary nebulae, gentle giants, breathe their last. For stars like our Sun, the red giant phase marks the beginning of the end. As the star runs out of helium to fuse, its outer layers become unstable and are gradually ejected into space. This ejected material forms a beautiful, glowing cloud of gas and dust called a planetary nebula. Planetary nebulas have nothing to do with planets. They got their name from early astronomers who thought their round shape resembled planets. These nebulas are relatively short-lived, lasting only a few tens of thousands of years. Section 7. White dwarfs, stellar remnants. In the vast expanse of the cosmos, stars undergo a fascinating life cycle, and one of the most intriguing stages is that of the white dwarf. At the center of a planetary nebula lies the remnant core of the red giant star. This nebula, a beautiful and colorful shell of ionized gas, is the last breath of a dying star. This core, now incredibly dense and hot, is called a white dwarf. Despite its small size, it contains a mass that is nearly equal to that of our Sun, compressed into a volume similar to that of Earth. White dwarfs are about the size of Earth, but with a mass comparable to the Sun. This means that a single teaspoon of white dwarf material would weigh tons on Earth. They are incredibly faint, shining only from residual heat. Over time, this heat will dissipate, causing the white dwarf to cool and dim even further. White dwarfs are the final stage of evolution for stars like our Sun. After exhausting their nuclear fuel, these stars shed their outer layers and leave behind the dense core. They will slowly cool and fade over billions of years, eventually becoming black dwarfs. This process is incredibly slow, taking longer than the current age of the universe. Black dwarfs are hypothetical objects as the universe is not old enough for any white dwarfs to have cooled down completely yet. These theoretical remnants would be cold, dark, and virtually undetectable, marking the true end of a star's life cycle. Section 8. Supernovae, the explosive end. While stars like our Sun end their lives relatively peacefully, massive stars meet a much more dramatic fate. When a massive star runs out of fuel, its core collapses rapidly under its own gravity. This collapse triggers a runaway nuclear reaction that releases an unimaginable amount of energy. This energy blasts the star's outer layers into space in a colossal explosion called a supernova. Supernovae are among the most violent events in the universe. They can briefly outshine entire galaxies and release more energy in a few seconds than our Sun will emit in its entire lifetime. Section 9. Neutron stars, cosmic lighthouses. After a supernova, the core of the massive star may survive. If the core is massive enough, it will collapse further, compressing protons and electrons into neutrons. This creates an incredibly dense object called a neutron star. Neutron stars are only about 20 kilometers across, but they can have a mass twice that of the Sun. Neutron stars are fascinating objects. They spin rapidly, emitting beams of radiation from their magnetic poles. If these beams are pointed towards Earth, we see them as pulsars, rapidly flashing sources of radio waves. Section 10. Black holes, gravity's triumph. If the core of a massive star is even more massive than that which forms a neutron star, gravity will continue to compress it until it collapses into an infinitely small point called a singularity. This singularity is surrounded by a region of space-time where gravity is so strong that nothing, not even light, can escape. This region is called a black hole. Black holes are among the most mysterious and intriguing objects in the universe. They are invisible to telescopes, but their presence can be inferred by their gravitational effects on nearby stars and gas. Section 11. Conclusion. The circle of stars. From their birth in nebulas to their dramatic deaths as supernovae, stars play a vital role in the universe. They are the factories that forge the heavy elements that make up planets and life itself. Their deaths enrich the interstellar medium, seeding the next generation of stars and planets. The life and death of stars is a continuous cycle of creation and destruction. It is a reminder of the vastness and wonder of the universe we live in. By studying stars, we gain a deeper understanding of our place in the cosmos and the fundamental forces that govern the universe.